We have really interesting presentations this afternoon, starting off with Frank, who's going to tell us everything we should have known about NUS, but actually didn't manage to learn along the way. So with that, Frank, I'm going to turn it over to you and let you have at it.
Splendid. Thank you so much. As we heard, we're going to discuss non-uniform sampling. And the content that we will see today has been drawn over 25 years of contributions from many wonderful people. But in particular, right now, I'd like to highlight Darcy and the organizers of this beautifully arranged seminar. And of course, thank Professor Reynolds, who helped make NMR the most awesome analytical technology that there is. And it's fair to say that that has had an impact not only on everybody who's listening right now, but for humanity at large. It's really incredible. And I'm going to whine for just a little bit, since this is called the Smart NMR Symposium. And with great luck, NMR is filled with brilliant minds like Professor Reynolds. Now, in my case, I got to work alongside of folks like Ad Bax and Louis Kay and Stefan Greshek. And so on the one hand, that has been a remarkable experience and an incredible honor. But the corollary is that for my entire career, I've always been the dumbest person in the room. So I hope you'll listen to the rest of the content with some tolerance, but that you'll have some fun questions after. Okay, so time domain, frequency domain. In the time domain, we have a signal that extends over all the points in the data, roughly speaking. Whereas when we use the Fourier transform to generate a spectrum, we manage to concentrate the signals and separate them from the baseline so that both the signals and the noise can generally be identified readily. But there is very little or no difference in the information content between these two cases. And so in one sense, all of the hand-wringing that's involved in generating a spectrum is just for the convenience of being able to analyze it visually. That said, let's talk a little bit about the properties of digitally sampled signals that we use in NMR, and in particular, the property that we're going to talk about is the maximum achievable resolution. Now, the maximum achievable resolution in digitally sampled NMR data depends on the duration of time between the first point that we acquire and the last point that we acquire. And we can understand this pretty readily in a graphical way. So what you'll see here are two signals that are almost identical in frequency. And up here is the time domain version, here's the frequency domain version of these two signals. Now, if we measure only over a short duration, it's very difficult to tell the difference between these two signals. And we have to let them evolve for some time before the difference in these two frequencies becomes readily apparent. And so this is why the duration of the measurement is what determines the maximum resolution that we can achieve with a measurement. Now, in the directly detected dimension, we have an RF pulse and we acquire a bunch of points. And the amount of time it takes to measure data in the directly detected dimension depends simply on this duration. So if this duration is a second, it takes a second whether we acquire 100 points, 1,000 points, or 1,000,000 points. But as we know, in a multidimensional experiment, we will have some collection of pulses which we vary in a systematic way. And for each one of these variations, we acquire another 1D spectrum, and that encodes information in the indirect dimension of this experiment. And so we have a collection of these measurements that we generate in the time domain. We Fourier transform all those rows to generate an interferogram, and then we Fourier transform all the columns of the interferogram to generate a spectrum. And so what that means is that the amount of measurement time that's required is based upon the number of times we have to repeat this 1D measurement. So that's in contrast with the directly detected dimension, where the amount of measurement time required is just the duration of the measurement. And so if we want to shorten the experimental measurement time of a multidimensional experiment, one of the ways that we can do this is by simply skipping over some fraction of the 1D measurements that we would make in the course of a multidimensional experiment. So that will decrease the measurement time, but as we will show, it will conserve the maximum achievable resolution. The challenge is that when we measure non-uniformly sampled data like this, the indirect dimension has gaps in it. And so when we Fourier transform the indirect dimension, we get a spectrum with artifacts that isn't suitable for direct analysis. And so we have to resort to other methods to reconstruct the data. Now, regardless of which method that we use to reconstruct the data, we can think of the reconstruction methods as a way to take the missing points that have been skipped over in the acquisition and find a way to replace those missing points with data. And generally speaking, any mathematical procedure that we use to replace missing data points in the interior of the data, we can also apply to add synthetic data points at the end of the data. And what this means is that the reconstruction methods that we will talk about today can be used on both conventional and non-uniformly sampled data. They can be used on conventional data to extrapolate the signals as an alternative to linear prediction, and they can be used on non-uniformly sampled data to both extrapolate and interpolate the missing points. And how that happens and what details are important is what we will discuss. And by extrapolating the data to add additional points, what we do in effect is increase the apparent duration between the first and last point, and therefore we increase the apparent resolution of the final result. So to understand all of this, it's useful to start by discussing the details of the discrete Fourier transform that we use to reconstruct conventional spectrum. And in the form that we use it for NMR data, looks like this. The NMR data that we want to transform is little x of t. And to perform the Fourier transform, we multiply that time domain data, little x of t, by a Fourier term, add up all the points, and that generates 1 point in the corresponding spectrum, big F of t. These Fourier terms are cosines and sines. They have a real part and an imaginary part, and each one of these Fourier terms corresponds to a different position in the corresponding spectrum. So to actually discuss how the mechanism of the Fourier transform works, all of the math is done with complex data, but for simplicity, we're going to look at an example with just the real parts shown and the imaginary parts will be hidden for simplicity. So we'll start with simple data, time domain data to transform, and to generate 1 point in the Fourier transform, we have a Fourier term, we multiply it by our time domain data, that forms a product. Now, the Fourier terms, as we discussed, are sinusoids, and we know our NMR data are also sinusoids. And generally speaking, when you multiply two different sinusoids together, the product that you generate has exactly balanced amounts of positive and negative intensities. So when you add up all of these points, you get something close to zero. And in the subsequent little animations, I will monitor the amount of positive intensity and the amount of negative intensity with these little bar charts. So what happens in the Fourier transform? For each Fourier term, we multiply that Fourier term by our time domain data. That forms a product. We add up all the points in the product to generate one point in the corresponding Fourier transform. So what happens is that only in cases where the frequency of the particular Fourier term matches one of the frequencies in the time domain data, that we get a product that's either predominantly positive or predominantly negative, so that when we add up all the points in the product, we get a peak in the spectrum. Nice and straightforward, easy to understand. Now, in practice, with a conventional NMR experiment, in the indirect dimension, we acquire a limited number of points, and the signal that we get is truncated. When we use this same Fourier transform mechanism on data like this, which is truncated, the product that we generate between the Fourier term and our truncated experimental data is also truncated. And what this means is when we add up all the points in this truncated product, we don't get ideal cancellation of the positive and negative intensities anymore. And so the corresponding spectrum that we get, even though in this case there is no decay in the data at all, the corresponding spectrum gives us this artificially broad line. And it also gives us these regular truncation wiggles. Okay, so that isn't great, but we live with this. This is what we see every time we process conventional multidimensional data. Now, in the case of non-uniformly sampled data, the data that we get looks like this. The missing parts that were skipped in the non-uniformly sampled acquisition are replaced with zeros. And so the product between the Fourier terms and the experimental data has these gaps in it. And when we add up all the points in the corresponding spectrum or corresponding product, we also don't get ideal cancellation between the positive and negative intensities anymore. And so the kind of spectrum that we generate has what seems to be these noise artifacts in the baseline. But in both of these cases, conventional data and the non-uniformly sampled data, both of these are sampling schedules, and both of them have these characteristic artifacts. And every peak in these spectra will have the same artifacts. A big peak will have these artifacts, but they'll be bigger. A small peak will have artifacts in the same shape, but they'll just be smaller. We've spent a lifetime looking at these conventional artifacts, but when we look at these non-uniformly sampled artifacts, they're very troubling to us. So why do we do it? Well, as we mentioned, this non-uniformly sampled data conserves the duration between the first and last point that we had with this original data. So it generates lines that are just as sharp as the original measurement. But we have this annoying apparent noise in the baseline, which we know is proportional in size to the size of the peaks. So we'd like to find a way to take advantage of these sharp signals, but compensate for these reconstruction artifacts. There are many really good ways to do this. Perhaps the most widely known one is iterative soft thresholding, or IST, that was popularized by Sven Heberts at Gerhard Wagner's group. And most recently, the reconstruction method called SMILE has performed particularly well in the NUSCON reconstruction contest. So I'm going to talk about these two methods today. But first, about IST. Now, as we mentioned, the reconstruction artifacts in any kind of spectrum, whether they are conventional or non-uniformly sampled, the reconstruction artifacts are proportional to the size of the signals. And so we can take advantage of this fact to generate a cleaner reconstruction as follows. We'll start by a regular Fourier transform of our data that has these reconstruction artifacts in it that are due to the sampling schedule. And we'll choose a threshold, which we know is guaranteed to be above the largest of any of these artifacts. And once we've chosen a threshold, we will remove a small part of the intensities above that threshold and accumulate them in another spectrum. Then we will reduce the threshold, inverse transform this reduced result back into the time domain. Any parts that were originally 0 in the sampling schedule will be set to 0 again. We will forward transform that result back into the frequency domain and repeat this procedure over and over again, each time transferring more and more of the largest intensities into the accumulated IST spectrum. And we can stop at any time, and whatever residual is left here, we can optionally add into the final result so that we can be certain this final spectrum that we generate captures all of the intensity that we started with in the original data. So this method is easy to understand and to implement. And because of the way it works, any nonlinearity that the method has is primarily for the smallest intensities. And so as a result, the linear behavior of this particular kind of reconstruction is very good. And these are intensity versus intensity for 2D spectra reconstructed by IST compared to a regular Fourier transform. So these results are nicely linear. Now, the alternative method that we'll talk about today is a parametric method called SMILE, and this was developed by Jin-Fei Ying in Ad Bax's group. And SMILE starts by generating a series of ideal time domain signals at the same resolution as the original measured data. And whatever sampling schedule was used on the original data is used to resample these ideal signals. And then they are Fourier transformed in the same way that the experimental data is. So this gives us a way to look at an experimental data and figure out for a given observed line width what the actual original decay was. And this lets us very accurately make good approximations of the data in a sequential way. So we can start with a complicated signal like this one and approximate it as a series of ideal time domain signals that are Fourier transformed in the same way as the experimental data. So what you're seeing in this series of postage stamp plots are all the different individual ideal signals that SMILE is using to decompose this measured data until the difference between the measured data and model is as small as we wish it to be. And using this procedure, we can approximate peaks of any shape, regardless of whether they are ideal or not. So in the case of non-uniformly sampled data, as we generate these models, we use them to fill in the missing points and eventually get a time domain data set that has all of the interpolation and optionally extrapolation that we need to generate a beautifully clear spectrum. So that works very well. Now, as I mentioned, we can use these techniques on conventional data as an alternative to linear prediction. And linear prediction, as we know, is applied to individual 1D vectors. And linear prediction is a nonlinear technique, which means it treats large signals in the presence of noise different than it treats small signals in the presence of noise. And so as a result, when we process different vectors through the cross-section of a peak, the vectors through the highest parts of the peak will be handled slightly differently than vectors drawn from the edge. And so in practice, when we use linear prediction in this way, we often get small distortions around the base of peaks. Whereas multidimensional reconstruction methods like IST and SMILE do not suffer from this problem, so we get extrapolation results that are potentially much better. So here's a 2D case, and forgive me, it's biomolecular. Here's a biomolecular 3D case. So originally measured data that were processed with linear prediction, or data that were extrapolated by IST in the two indirect dimensions. So better result. And in 4D, the case is even more remarkable. So here's a region from a 4D reconstructed by FT, by linear prediction, by IST. And so there's much better artifact suppression with this method than with the other two. Now, let's turn our attention to a specific small molecule example. And this was an example that was provided by our colleagues at Pfizer, Greg Walker and Kathy Farley. So the examples that we're going to see are of this bile acid here. And to figure out what's going on, we're going to highlight the details of this little doublet down here, which is drawn in an expansion. Okay. This particular 2D proton carbon spectrum was measured with 1,024 complex increments in the indirect dimension, which in this case took about 4 hours. And at this resolution, you can look at this doublet and see things nicely separated. Okay. Now, if we had only acquired 128 points instead of this full 1024 points, the spectrum that we generate would look like this. So now we have a measurement time that's only half an hour, but whereas in this high resolution spectrum, we could tell the difference between these two peaks in this doublet, we can't do that quite so readily when we reduce the measurement time just by truncating the measurement. Whereas by contrast, if we use non-uniform sampling and a particular sampling schedule like the one shown here, and in this case, IST reconstruction, we can get a result with half an hour of measurement time that's as good or better than the one that took 4 hours. So in a pharmaceutical company, this is a substantial benefit because a result like this that takes half an hour can be delivered in the same day, whereas a spectrum that would take 4 hours to measure would generally be deferred to a nighttime, an overnight measurement. Okay, and I will tell you that this ability to measure good spectra with non-uniform sampling in this way is so reliable that there are many sites that will use non-uniformly sampled acquisition as the default for routine walk-up measurements. And folks who use these measurements don't even know that the non-uniformly sampled technique is being used. Now, let's look at some variations. So this is one particular sampling schedule. Here's an example where instead of using IST, we use the SMILE method to reconstruct the spectrum, and we still get beautiful resolution. And for all intents and purposes, the spectrum is about as good to analyze. If we use a different sampling schedule, which samples heavily at the beginning and end of the data, we get a spectrum that's also very similar, and we can differentiate what we need. Or if we use a sampling schedule that samples very heavily at the beginning and more sparsely at the end, we still get a spectrum that's about the same for all intents and purposes. So why is it that all of these sampling schedules deliver about the same result? Well, for the measurement that we saw, the original signals in the indirect dimension don't decay very much. They only decay to about 2/3 of their original intensity. So these different sampling schedules don't really capture very different amounts of signal. They don't capture different amounts of signal. And there's a little bit more to this, but let's look at a couple of confirmations of this. What we see here are volume measurements made on the original uniformly sampled data compared to volume measurements made on the conventional data with linear prediction, the non-uniformly sampled data reconstructed with IST and 3 different sampling schedules, and the random non-uniformly sampled schedule also reconstructed by SMILE. Okay, so all of these methods have about the same uncertainties in determining the volumes, and the uncertainties in the volumes are due primarily in this case to systematic distortions in the measured spectrum, not to the reconstruction, which is why all of these methods give about the same results. And the non-uniformly sampled spectra give results that are about as good as results that come from the conventional data with linear prediction. Now, when we look at the reproducibility of frequencies that come from this method, what we see that there is absolutely no difference at all between any of these cases. And this is something that's important to consider. This is a feature of NMR that we often forget about, but in practice, as long as you can tell that there is a peak there, you can measure its chemical shift to great precision. And this is why, in most cases, we still get better performance from sampling schedules that capture more intensity compared to sampling schedules that are arranged for higher resolution. Okay, now here is possibly the most important take-home message of our discussion today. How many increments should I measure? Well, in order for non-uniformly sampled reconstruction to work, there are a few criteria. One is that the underlying data has to be sparse, which we can take to mean that the spectrum has to have more empty space than signals. But the other thing is that we have to measure enough signals to account for the number of samples, or we have to measure enough samples to account for the number of signals in the data. And to demonstrate this, and forgive me, it's a biomolecular example, I'm going to show you examples of a 2D reconstruction on data which start with 378 peaks and versions of that same data with reduced numbers of peaks, so 189 peaks, 94 peaks, 18 peaks. And what we will do is gradually reduce the non-uniform sampling fraction and see what happens. So at 90% sampling, all 4 of these results are about as good. 80%, everything looks good. 75%, 70%, 65%, everything still looks beautiful. At 60%, 55%, 50%. Okay, so far so good. Now 45%, 40%. 35%, we can start to see artifacts appear in this spectrum with the largest number of peaks. At 20%, we can start to see artifacts appear here. And now at 15% and 10%, this case here, whereas the spectrum that has only 18 peaks still looks good at only 5% sampling. And this is not surprising. We can understand this by considering that each peak represents a certain number of parameters, and we need enough samples to describe that number of parameters. And so in this graph, this illustrates what we just saw. Sampling density with respect to a particular number of increments. This vertical scale means a worse and worse reconstruction. And so the data with large numbers of peaks gets worse more quickly than data with small numbers of peaks. However, if we represent the case in terms of the number of peaks, what we see that the ratio of samples to total number of peaks or total number of peak parameters is about the same for all of these cases. So in other words, we need roughly 10 or 15 times the number of samples as we have signals in the data. So that is perhaps the most critical take-home message. And so quick comments, we've been living with the effects of sampling schedules for a long time. Non-uniform sampling gives us a way to generate sampling schedules with different strengths and challenges. And most critically, sampling density is a misleading measure. We should always consider density relative to the number of signals in the indirect dimensions. We have to measure enough increments to account for the number of signals. And no matter what, we have to capture a sufficient amount of intensity to see the peaks of interest. So that is the overview. Hope it was interesting. Looking forward to your comments.